All right, AP Chemistry folks, this is another edition of AP Chemistry at Dallas Center Grimes. This is Unit 6 on chemical bonding, and we have two different pieces of chemical bonding. We have Chapter 9 and then Chapter 10. Chapter 9 is the basics, where we look at the different kinds of chemical bonds, ionic, covalent, stuff like that, where when we do our Chapter 10, we get into more of the VSEPR theory, valence shell electron pair theory, valence bond theory, molecular geometry, hybridization, and some other more difficult stuff. Now, as we went through the learning objectives in class, the bonding basics is the initial stuff, most of the stuff that we learned in general chemistry. We have Lewis structures for our second objective, and as we talked, we said that in order to be able to do bond enthalpy, VSEPR theory, or valence bond theory, all of those rely on our ability to write Lewis structures out correctly and without a whole lot of difficulty. So there's that. Jump right into the first one, the bonding basics. We can start looking at the very initial work that we do with Lewis symbols. So Lewis dot symbols, we have some elements that are neutral, some that have ions. We start off with the element symbol, and then we draw around it the number of valence electrons it has. An iodine with a negative charge would have all 8. Or if we did something like sodium here, it'd have a single one, and then sodium with with a positive charge is going to have no valence electrons on it. We could do some others here. Magnesium. Let's do aluminum. 1, 2, 3, and aluminum with a positive 3 charge would look like that. So we have the different kinds of bonds. An ionic bond is formed from the transfer of electrons, where covalent bonds are the sharing of electrons. Number 13. We can start looking at some properties. Sodium chloride can conduct electricity when it is molten or dissolved in water, and the reason is that this allows, either of these situations allows for the electrons to be dissociated or not locked up in the crystalline lattice. There's a word for that I'm trying to think of, escaping me at the moment. But they're not locked up in the solid, and they're free to move. So those are the correct answers there. Use the Lewis dot symbol to show the transfer of these things. So we can do maybe just one of these. I will do potassium and sulfur. Potassium has 1 valence electron, and sulfur has 6 valence electrons, which means that we have to have a second potassium. Potassium gives the electrons to sulfur, so we end up with sulfur with all 8 valence electrons. Potassium and potassium, and we show the charges. Charges are absolutely necessary for full credit. If you don't show the charges, you don't get full credit. For the positive one, we do not have to have the 1 there. It's just a positive, it's implied. Lattice energy is the amount of energy required to break apart an ion into their gaseous, or the ions in an ionic compound in their gaseous form. Now, it's important that they're gaseous, not really in terms of our physical understanding of what happens, but in terms of the value for lattice energy. If they're gaseous, we know that there aren't going to be any other kinds of attractive or repulsive forces, and so we know that the amount of energy required to do that is going to be the same kind of energy for any kind of element involved, as if we have that common gaseous ion piece to it. This is also related to Coulomb's law, which is the electrostatic attraction between two ions. And then if the idea here is that as lattice energy increases, so does the electrostatic attraction between those two different ions, which is what Coulomb's law is. which one has a higher lattice energy, and then again, which one has then a larger amount of, or a larger value for Coulomb's law. If we look at A, we have magnesium and oxygen. Magnesium oxide is going to be the larger one of those two, potassium chloride, because of its larger charges. Remember that when we identify or when we rank lattice energy, we first look at the charges and then we look at the size of the elements involved in the bonding. So these are going to be have value or have larger charges, so it's going to be the larger lattice energy. Here we have the exact same charges, positive 1 and negative 1, positive 1 and negative 1, and so we go ahead and look at the size of the gas molecules, of the ions. And lithium is going to be the same. Fluorine is going to be a smaller atom. Since fluorine is a smaller atom, there's going to be a greater attraction between the two, and so it is going to have the higher lattice energy. Magnesium nitride and sodium chloride, this is an easy one. Again, we have positive 2 and negative 3 for the charges here, and so a much larger lattice energy for that one. Single, double, triple bonds. So single bonds is the sharing of 2 electrons, like in fluorine. Looks like that. The Lewis structure. Double would be oxygen, and triple would be nitrogen. So sharing of 4 electrons, sharing of 6 electrons. And as we increase the number of bonds from single, double, triple, the bonds shorten. So we have the atoms closer together. All right, we have properties. Ionic compounds are soluble in polar solvents. They conduct electricity well in aqueous solution. They also conduct electricity in their molten form. They have a high melting point. They have a crystalline structure. They have a high heat of formation. And there's a couple other here that we looked at when we did our notes on those. Covalent, basically the opposite. Low melting point, often liquids or gases at room temperature. No crystalline structure. Does not conduct electricity ever. Polar covalent compounds would dissolve in polar solvents like water, so this brings up the idea of likes dissolve likes. So polar dissolves polar, or polar dissolves ionic. Nonpolar dissolves nonpolar. We're looking at the difference in electronegativities for question number 35. It asks us to identify which has the largest ionic character or versus the covalent one. So we have a lot of different ones to choose from. And this is put in order of smallest ionic character to largest ionic character. And so what we do is we use the electronegativities of the values of the elements and do some subtraction. So lithium and fluorine. Lithium has the electronegativity of 1.0. Fluorine is 4.0. The difference there becomes 3.0. The others I don't know off the top of my head, but I went ahead and I did the calculations ahead of time. Nitrogen is going to be 0 because whatever the electronegativity of nitrogen minus itself is going to be 0. Sulfur dioxide is 1, chlorine trifluoride is 1, potassium oxide is 2.7, lithium fluoride is 3. So we're putting them in order of increasing electronegativity values. And we can see this right here. We have 1.0 and 1.0 for those. And I have a note here. They both have 1.0 if we round the electronegativities to the nearest tenth. But if you look up values that have these electronegativities at the 100th decimal, you're going to see that SO2 is slightly less than 1, while ClF3 is slightly more than 1. So that's how I was able to put those two in the correct order. All right. Now we get into some Lewis structures. Oh, I never made this fix, ladies and gentlemen. If we go to letter D, this 2 here should be a negative sign. So let's go ahead and make that change. Negative. And when we practice these in class, we went through the steps that you're going to use in order to come up with the correct answers. And I'm going to maybe skip ahead through some of those steps and not go over them individually for each single element. Here is A, nitrogen trichloride. It's going to look like this. We have oxygen, this compound. It'd be like this, sulfur, oxygen. We have H2O2, which is kind of a funky one. We have oxygen here, hydrogen, and hydrogen. We have the acetate ion. Now this is an organic compound, and we can come up with the correct Lewis structure somewhat by looking at how it is organized, and that's why it's organized this way. So we can see carbon is attached to 3 different hydrogens. It's attached to a carbon, and this carbon is attached to 2 different oxygens. And this does not work, it turns out. And I could go through and do formal charges and show you the inventing and destroying of electrons, but it's much easier to think about it this way. We said at the beginning that carbon will always have 4 bonds. And that is the only way it's going to be able to get 4 bonds out of there, because this one already has the 4 bonds. So here's 1, 2, 3, 4. 1 oxygen there, 1 oxygen there. The overall charge is -1. So there's that. CN2 is going to look like this. Ooh, I apologize. Oh, that's why this is also negative. That makes sense. 1, 2, 3. Nitrogen. Uh-oh, that happened. So this is the only one that is an exception to that guy. I'm sorry. So there's cyanide. It has 3 bonds there, and that is the only one. I promise. I forgot about that one. All right, then we have this one here. Carbon, 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 carbon. Nitrogen, hydrogen, hydrogen, hydrogen. And we'll just connect those lines to show the other hydrogens. And this is going to have a +1 charge. And I'm still bothered by this one here. I completely forgot about that exception to that rule. And that's the only one. More Lewis structures here. Let's see. Trying to figure out how many of these I should do. Let me just get them up on the screen real fast for you so you can see them. There is that one. We have Si. Those are all hydrogens. There is the hydroxide. That's a Cl there. And this last one. Those are all hydrogens. All right, so anytime I have a line there with nothing connected to it, it's indicating a hydrogen. These acids are weird. It's going to look like that. And we'll talk more about why it has this Lewis structure when we get into our acids and bases unit. All right, so there's those. Give you just a moment. All right, 3 resonance structures of ClO3. And now Cl, going with our method before, let's go through the work on this one because it's going to be a little bit tricky. ClO3 has a total of 7 plus 18 plus 1 valence electrons. That gets us 26 total electrons to work with. Here is chlorine, single bonds here, oxygen, oxygen, oxygen. Fulfill octets, here's 1, 2. If we count all of this up, there's 8, 8, 8, and then there is 2 more there, so that does get us our 26 valence electrons. But there is a problem with this, and this is where I can introduce formal charges on this video here. So if we look at the formal charges, oxygen has a formal charge of -1 here, -1 here, -1 here, and this has a formal charge of +2. Now all of these things equal the -1 that we're after, but we can come up with a lower value for the formal charges. If we put a double bond here, get rid of this, and we put another double bond somewhere else. Now we can go through and see that we still have, didn't have to get rid of those, we still have our 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 26 valence electrons, but now I have a formal charge of 0 here, 0 here, 1, 2, 3, 4, 5, 6, 7, 0 here, and a -1 formal charge on this side. So that's going to be a preferable Lewis structure to the one previous. We want to minimize those formal charges. So we have that resonance structure. We have this resonance structure. We have the final resonance structure. Looks like that. So those are the 3 resonance structures for the chlorate ion. So this is our introduction on this video about formal charges. Remember, the formal charges are valence electrons minus our lone pairs, or not lone pairs, we just say electrons. Electrons plus bonds. So here I have 6 valence electrons for oxygen, and I have 1, 2, 3, 4, 5, 6 electrons. There's my 6, and then minus the bond as well. So if we do this here, like that, we get a -1 for formal charge on that guy. All right. I'm going to skip 55. You can too. It's possible, and there's more than 3 resonance structures for this atom, but it's beyond what we need to know. 58. Give 5 examples that do not satisfy the octet rule. Write a Lewis structure for each. This could be a number of things. You could do boron or beryllium dichloride, boron trihydride, sulfur hexafluoride, phosphorus pentachloride, xenon tetrafluoride, xenon difluoride. All of those would work. And we're going to have plenty of time to practice those exact ones later, so I'm not going to do the Lewis structures for them now. And here is a perfect example. Here is beryllium dichloride, and beryllium starts out with 2 valence electrons. And we can see the sharing of electrons here. This is the old way, and the reason why I'm doing it the old way is to show you that beryllium can only form 2 bonds. It only has 2 places where it can form those bonds, so that's why it turns into this. 2 valence electrons, 2 bonds. All right, now we can look at some of these expanded octets. All right. Here is xenon difluoride, xenon hexafluoride, xenon, let's see here, fluorine, 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 and what's that oxygen going to do? And then we have here is there one or two? One oxygen there. So there's the oxygen. Now we can start looking at our work here. Let's do the actual math on this one here. We have 8 plus 6 plus 28. That gets us 14 plus 28 equals 42. And if we go through here, we have 8, 16, 24, 32, 40. So I need to have 2 electrons there. And let's see if that's how we like our formal charges. So we have 1, 2, 3, 4, 5, 6, 7 here. So we have a positive 1 formal charge on the xenon. And here I have 1, 2, 3, 4, 5, 6, 7. So a negative 1 formal charge on the oxygen. Again, it's the number of valence electrons, 6, minus the total number of electrons and bonds. So 6 minus 1, 2, 3, 4, 5, 6, 7. That gets us a negative 1. And so this is going to be a less favorable Lewis structure to what it could be because we have formal charges. If we take out the electrons here and put it into a bond instead, I have 1, 2, 3, 4, 5, 6, 7, 8, the formal charge of 0 on xenon, now 8 minus 8, and now oxygen is 6 minus 1, 2, 3, 4, 5, 6, 0. So there's the correct Lewis structure for that one. Get rid of those formal charges. So for the next one, I have xenon dioxide, difluoride. And this is what it's going to look like here in the end. And we can do the formal charges on this one again. We have 8 for the xenon, and then we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8 on the xenon. And then we can do the same work with the oxygens and see the formal charges on those would equal 0. So that is that one there. All right, these two are a little bit more difficult, but kind of fun. Antimony pentachloride, a pretty straightforward one. We have antimony in the middle and chlorines around. Antimony starts with 5 valence electrons, so there's the 5 bonds. We could also do it the way that we've talked about. So we have 5 here plus 35 here gets us to 40. 8 valence electrons around each of these. 8 times 1, 2, 3, 4, 5 is going to get our 40 valence electrons that we start with, and we should be good. All right. 2 last ones. SC. Let's actually go through the work on these. Selenium is going to have 6 valence electrons. Double check that because it's in that same group. There's 6. Then we have 4 times 7. It gets us 28. And then we get 34 electrons there. On this side, we're going to have 7 times 6 is 42. Plus 6 gets us 48. So let's do this. Selenium, 1, 2, 3, 4. Fluorine, 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 fluorine. Now if we go through and do octets on fluorine, we have 8 for each of them. And so that gets us 32 valence electrons, 8 times 4. And we have 34 that we need, so I'm going to put 2 more electrons on that selenium. We have selenium with the 6 fluorines on it. We have 48 valence electrons total. 1, 2, 3, 4, 5, 6 times 8. There's all 48, and so we're good there. Bond enthalpy. So this is just a quick thing for our Learning Objective 3. And there are only 2 problems on Learning Objective 3 that we have, and this is one of them. So bond enthalpies are another way that we can estimate how much energy is either required or released in a chemical reaction. And it's based on the idea that it requires energy to break bonds, and energy is formed or released when energy is released when bonds are formed. So we can use those values, the bond enthalpy values, to be able to calculate the overall enthalpy of a reaction. Now, it's a little bit more of an estimate this way than using the heats of formation, because when we have double and triple bonds, it takes a different amount of energy to break the first bond and the subsequent bond and so on. That's not necessarily true in diatomics, but in things like carbon dioxide or ethene or things like that, it will require more for each subsequent bond. So we're using averages as opposed to actual values. So we have number 972. And I actually didn't do this one here. You can do this one if you want. But the actual work for this is somewhat involved. The first thing that we have to do is write out the Lewis structures. So we have C, the C. And there are 2 of those, 7 of those. And 4 of those. And 6 of those. So if we total things up here, we have 2 carbon to carbon bonds. We have 12 carbon to hydrogen bonds. And we have over here 7 oxygen to oxygen bonds. And we can look up the values of these in the table. Carbon to carbon has 347 kilojoules per mole, and the carbon to hydrogen 414 kilojoules per mole. And then the oxygen to oxygen bond, because diatomics can be measured exactly, this will get us 498.7 kilojoules per mole. Over here, I have a total of 8 carbon to oxygen bonds. I have then over here a total of 12 oxygen to hydrogen bonds. So here's my dividing point. We have here then at 799. Now if you're doing the work on your own and you're coming here to check it like you're supposed to, you're going to notice maybe that you have a different value for this. That's because at the bottom of the table, there's an asterisk next to the carbon to oxygen bond here. There's an asterisk there. Put it right there. And then it says in the carbon to oxygen bond in carbon dioxide, it's this value. Not whatever value is listed in the table. 12 oxygen to hydrogen bond is 460. Now, since each of these is represented as a breaking of bond, instead of doing products minus reactants, we do reactants minus products. So how much does it take to break them? And then how much energy do we get back from putting them together? So if we do the math here, we end up with 8,459 kilojoules per mole. And on this side, we end up with 11,912 kilojoules per mole. Reactants minus products gets us our final answer of negative 3,453. So there's a final answer there, and we could go to the enthalpies and do products minus reactants for this as well, which I have not done yet, so I will allow you guys to do that on your own. All right, now we go on to this more practice. This is actually an old quiz that I would give. And so it has both learning objective 1 and 2 and 3 on it. And so let's just go over some things very quickly, some stuff that you've already looked at, and some stuff that'll be maybe new. So we have metals and nonmetals make ionic, different characteristics of ionic compounds. What keeps them bonded together? This is a new question. We haven't seen this one yet. And this is the fact that in ionic compounds, we form ions, and those ions are going to have positive and negative charges, like sodium and chlorine, positive and negative. Those attract to one another, and this attraction turns out to be very, very strong. This is based on Coulomb's law, that we have positive ions and negative ions attracting together. Covalent, nonmetals and other nonmetals. We have the different properties of them. The new question here is that the sharing of electrons allows covalent compounds to be bonded together, is that when they share those electrons, they have a full outer shell. Organize these have increasing lattice energy. So I'm going to first look at charges. And so if I go through the charges on this one, you can see that this is positive 1 and negative 1, positive 1 and negative 1, positive 2 and negative 2, positive 2 and negative 2, positive 1 and negative 1. And so I'm going to look at these two first, because they are the ones with the largest charges. I'm going to use the one that's smaller first. Smaller atoms have less electron shielding, so they're able to attract to one another more tightly. So I go with calcium chloride because it's the smaller of the two. That's going to be the strongest lattice energy. Then I go to the next one. After that, I go to my positive 1 and negative 1, and again, put them in order of decreasing atomic radius. So cesium iodine are going to have the largest radii, and then we have the sodium chloride and the sodium fluoride. Lua structures, none of this is new. I guess I can take just a moment and put up the answers. Silicon, ooh, I got red now. There's the chloride. Nitrogen trihydride, also known as ammonia. There's two dots there. Nitrogen triple bonded to another nitrogen, and then sulfur difluoride. So those are them. Lewis structures for these. These are going to have probably some kind of a weird octet. And this is not a new one, but let's look at it again. We have 8 plus 28 gets us 34. If I look at my octets right now, each fluorine has a total of 8 valence electrons with the bond. So that's 8, 16, 24, 32, and the 2 electrons there. Here is ICl, PBr, look at this guy. Look at him. Isn't that adorable? Boron dihydrate. I don't know what kind of polyatomic this is, but it's some kind of a polyatomic. So let's look at this one. Boron has 3. We have 1 from each hydrogen, 1 from the charge. That gets a total of 6. Set it up so we have our 2 single bonds to the hydrogens because that's all they can make. And that's 2, 4. Got those 2 extra electrons there. Makes 6. And then we have another one. This is a good one too. Let's go ahead and do it. We have 7 plus 28 gets us 30, what is that? 35 minus an electron. So we end up with 34 total valence electrons. Here's chlorine. The fluorines each get an octet. They always have to have that single bond. So there's 8 in each of those. 8, 16, 24, 32. And there's my 34. Draw 3 plausible Lewis structures for the sulfate ion and identify which is correct using formal charges. So this is that idea of using formal charges. So we can go here. There is a plausible Lewis structure for this guy. Here's another one. Here's another one. I'm going to do more than 3 and show you which one is correct and why. There's some there. Remember we have this -2 charge here, so if we total up all the valence electrons, I get 6, and oxygen is also 6, so all of these are 6, so 6 times 5 is 30. We get 2 more electrons, so we have 32 electrons to work with. And in every single one of these, we're going to get that 32 electrons. Oxygen has an octet each time. So we have 8, 16, 24, 32. It's going to be true every single time. So now we start assigning formal charges. In this case, I'm going to have 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So that's a -1. All of these will have a -1 formal charge. Sulfur starts out with 6 valence electrons, minus 1, 2, 3, 4 bonds. That gets us a +2. +2 and -4 makes -2. That's what we're after. Everything's done correctly, but we can do a better job in minimizing formal charges. Next one. Here we have a -1, -1, -1. This oxygen has a formal charge of 0, so that's favorable. And now sulfur has +1. Starts with a 6, 1, 2, 3, 4, 5, a +1. Again, formal charges are the number of valence electrons. Oxygen has 6, minus the number of electrons and bonds that are on it. So if we go back to this one as the example, oxygen starts with 6 valence electrons, minus 1, 2, 3, 4, 5, 6 bonds. And we have, 1, 2, 3, 4, 5, 6 electrons, and a bond. Gets us -1. So that's where that -1 comes from. All right, so we've done better. Now we have -1, -1, -1, and +1. So we're down a negative, and now we're up a positive. That makes sense. So we're doing a better job of minimizing formal charges. So let's try this next one. In this one I have 0, 0, 0, and 0. That's how I got this one here. So we have electrons, 1, 2, 3, 4. 6 valence electrons, 1, 2, 3, 4, 5, 6 for that. So we end up with a 0 formal charge. Sulfur though, 6 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8 bonds, gets us -2. So we're doing better again, I guess. We only have one thing with a formal charge on it, and the other ones are 0. But here's a key point. If we minimize formal charges as much as possible, we want to make sure that any negatives go on to the more electronegative element, which is oxygen, not sulfur. Which brings us to the last one. Formal charge of 0 here, formal charge of 0 here, -1, -1, and a formal charge of 0 in the center. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So this is going to be the favorable Lewis structure for the sulfate ion. Now we can do bromate, and we can just skip to the correct Lewis structure because of our understanding of the formal charges. So here's bromine at 7. We have 18 here, 1 for that one, so we end up with 26 valence electrons. Here's bromine. There are our oxygens, and if we go through and add these, we end up with 24 and 2 electrons. That makes 26. And our formal charges are not going to be real fantastic. We have a -1, -1, -1, and +3. So let's see if we do some work here. Let's do another double bond here. Double bond there. 2 electrons. Again, we have our 8, 16, 24, 26 valence electrons. We look at formal charges. This is going to be 0, 0, -1. And this will be, I believe, 0. 1, 2, 3, 4, 5, 6, 7. So this is going to be our preferred Lewis structure. This actually is very similar to one that we did earlier. And we can then do bromine like that. And we can do bromine like that. Those are our Lewis structures. Don't forget to put polyatomics in brackets. All right. Oh dear, there's a bunch of them. Let's go ahead and move on. If after doing all of the work on this already, you need some additional help with carbonate and sulfur dioxide, feel free to come in and I'll work with you on those. We have another bond enthalpy problem, so we're back to learn objective 3. We can look at the different values we have here, and we have to draw out our Lewis structures first. We have three H, and we have N. All right, and we have 2 of those. So we have 1 nitrogen to nitrogen bond, 3 hydrogen to hydrogen bond, and 6 nitrogen to hydrogen bonds. And we'll just go through and do the work. I haven't done this problem yet, so I'm not going to do the math right now. You need to take 945. Now notice it says nitrogen-nitrogen bond. There's just one line there. All it's indicating that it's the nitrogen-nitrogen bond. Don't worry about the triple bond here that is missing. So 945 plus 3 times 436. And then we subtract that from 6 times 339. And actually I do have a calculator right now, so how about I do that and get the answer. And I get 219. So, if we go on through the next problems, we can look at molecular geometry now, which is learn objective 4. And we have the different kinds of geometries here that's broken down into individual steps. And I just kind of want to show you how each of these looks. We have our carbon dioxide, linear, and the big thing here is that we're looking at whether or not we have extra electrons on that central atom. And that will determine our electron geometry as well as our molecular geometry. And we notice here that we don't have anything extra on that central atom, just 2 things attached to it, so it's going to be linear. So how do these compare? They're the same because of the no unbonded pairs. Now if we do the same thing for beryllium dichloride, we end up with the exact same scenario. The one thing I want to point out here is that the double bonds don't impact the molecular geometry. So these two things have the exact same geometry. The double bonds just means that the distance between these two atoms is going to be smaller than the distance between those two atoms. So the same there. Lewis structure for iodine triiodide, or I guess that didn't make any sense. For these three iodines bonded together, we end up with this. And the electron geometry is going to be trigonal bipyramidal. And so we have 5 things attached to the central atom. 1, 2, 3, 4, 5 things attached to the central atom, which makes it trigonal bipyramidal. However, these 3 electron pairs are oriented around it in such a way that the 2 iodines are as far away from each other as they possibly can. So the 3 lone pairs repel it, so we end up with that. Ozone will look like this. It has the 2 electrons on here. This is wrong. I did that one wrong. It's trigonal planar. We have 1, 2, 3 things attached to that central atom to trigonal planar, and we end up with a bent molecular geometry because of the extra electron pairs there. Water, though, is going to be tetrahedral. We have hydrogen, hydrogen, 4 things attached to it, 1, 2, 3, 4, and it becomes bent because of the extra electron pairs. So that is our bent molecules. We have our trigonal pyramidal and trigonal planar. The difference here is the electron pair on the central atom. So there you go. The extra set of electrons here, the lone pair of electrons on the ammonia, are the ones that push the hydrogens away from each other, or I guess away from the electrons towards each other, which makes it into a pyramid form. And it has a tetrahedral electron geometry because of the 1, 2, 3, 4 things attached to it. Tetrahedral. No lone pairs on the central atom. Trigonal bipyramidal. No lone pairs on the central atom. Octahedral is going to be the same thing down here. We end up with all 6 things attached to the central atom, no lone pairs. So the electron geometry is the same thing as the molecular geometry. Now we get into where it's not. The distorted tetrahedron. Looks like this. And that extra electron pair forces it to be kind of a weird seesaw shape. Chlorine trifluoride. Is our T-shaped. So we have the 3 fluorines there and the extra sets of electrons forcing the fluorines into a T position. And then the bromine pentafluoride. We end up with a square pyramidal. So we have the square base and then the pyramid on the top because of that extra electrons there. Square planar is the last one. I'm going to do it this way. In order to picture these in 3 dimensions, refer back to the handout that you got with all of the different shapes on it and use that. So this just serves as an additional study tool to how to write these electron geometries, or to give you examples of which electron geometry and which molecular geometry is which. All right. Now we have all sorts of additional Lewis structure as well as valence bond theory. So we have the shape and valence bond theory, and so we have these things here: draw Lewis structure, polar bonds and resultant dipole moment, molecular geometry, valence orbital hybridization, and then we're going to identify the number of sigma and pi bonds. And this goes back to some of the stuff that we looked in class about double bonds versus single bonds, that's sigma and pi, and how that looks, and then how we deal with valence orbital hybridization. So we have our carbon, oxygen. Now remember, we have these different hybridizations. We have sp, sp2, sp3, sp3d, and sp3d2. And we can count up the number of things that are attached to the central atom and get the hybridization that way. So we have S1 and P1. Those ones are assumed, so we don't necessarily write them, but that helps us figure out how many things are attached to the central atom and what kind of valence bond hybridization. 5 and then 6. So in this case, I have 2 things attached to the carbon atom and the central atom, which is carbon, so that comes out to be sp hybridization. Over here, carbon has 4 bonds always. We have our sp2 hybridization for the carbon. And then we have the sulfur work there. We have 6 fluorines attached to it, so we have the sp3d2. That's sp2. Now we can look at the polarity of these things. This is a polar bond, and we point these towards the more electronegative element. But since the resultant vectors of the polar bonds are equal and in opposite directions, there is no polarity to this molecule as a whole. So we have a non-polar molecule. Even though the bonds are polar, the overall molecule is non-polar. Same thing here. We have the resultant vectors that look like this. I should use a different color. That's really messy. Sorry, guys. And we end up with all of the electronegativity differences being pulled in equal and opposite directions. And so this ends up being a nonpolar molecule as well. And it'll be the same thing for this one. So let's go on to one that maybe that isn't the case. H2O. We have, let's see here. Now with the hybridization, we include electron pairs in that discussion. So we have 1, 2, 3, 4 things attached to it. The hydrogens count 1, 2, 3, 4. So we end up with an sp3 hybridization. It's a bent molecule, and we can draw the vectors, the polar bonds. In this case, it is not equal. We can see that the electronegativity is being pulled towards oxygen. We end up with the overall electronegativity difference, so the polarity going in that direction just like that. And this end vector, this end resultant dipole moment, is something that takes practice and may not be absolutely necessary on quizzes or tests at this point, but we want to be able to get to the point where we can see where the electron density is going to be richest. All right, let's do these quickly. 4 hydrogens, 1 there, 2 there. That doesn't work. That's because there's, all right, so I'm going to do that. There we go. We have this carbon is sp hybridized, and these carbons are sp2 hybridized. And then we can look at the vectors. So another thing we can look at, we can talk about symmetry. This is not asymmetrical. It has symmetry to it, and so it is going to be nonpolar. Sulfur here. Let me see if I can draw that better. Sulfur. And it is going to be, oh, that guy, yeah. So we have so 1, 2, 3, 4, 5, 6. Yes, so this is the correct Lewis structure for the sulfur tetrafluoride. It is going to be 1, 2, 3, 4, 5, sp3 dehybridized, and it is going to be polar. The resultant dipole moment is going to be towards those electrons. All right. C2H4. Carbons are sp2 hybridized. Oh, I guess we can also talk about the geometry, right? I forgot about that. Let me go through all of these and I'll come back to the geometry. So there's that. It's going to be nonpolar, polar, nonpolar, polar, nonpolar, sp2, there's the fluorines. Nothing else on the central atom, so this is nonpolar. Here's this guy. Oh. We definitely have a polar here. The resultant dipole moment is going to be like that. And going back to the different geometries, this is going, so it depends on this one. If we look at this one, it's linear. This is trigonal planar. This is, I'm going to say seesaw because it's easier to write. That is distorted tetrahedron or seesaw. This is going to be trigonal planar. This is trigonal bipyramidal. And this is going to be trigonal planar again. All right. How many more of these do we got left here? All right, well, maybe I won't do all of them. C, that's bonded to H. O, there's that one. This one, it says the carbon atom, so we'll focus on that one. It is 1, 2, 3 sp2 hybridized. It will definitely be polar. It does not have that symmetry to it. And then we end up with a trigonal planar again for the molecular geometry on that thing. We have boron trifluoride. That'll also be sp2. Man, sp2 is a popular choice in this set. And this is going to be nonpolar. There is no asymmetry there. It is very symmetrical. And so we have trigonal planar again. We did this one before. Actually, I don't know if we did this on this or just in class. This is an easy polyatomic to write because carbon always has those 4 bonds. 1, 2, 3, 4. So that helps us identify the correct Lewis structure for that one. And man, it's another one. Okay, so it's again sp2. This is going to be nonpolar. And it is trigonal planar. Again. Hey, you're going to see this pattern here. sp2 is trigonal planar. sp3 is tetrahedral in electron geometry. So you can kind of keep track of those kind of similarities. This one here, COH. And this is sp3, polar, and tetrahedral. Fluorine bonded to fluorine. Put those around so we can see that it is sp3 hybridized. And this is why. Here's fluorine 1, 2, 3, 4 things attached to it. So there's sp3 hybridization. It is going to be nonpolar, and it does not have a molecular geometry because it does not have a central atom. Benzene looks like this. Where each of the individual points is a carbon atom, and each carbon atom has 2 hydrogens attached to it. So there's that. So we have our 1, 2, just 1 hydrogen attached to it. One, 2, 3, 4 bonds on each of the different carbons. And then we can look at this again, or look at the geometry as well as the hybridization. First of all, this guy is nonpolar. For sure, it's very symmetrical. We have another sp2 hybridization, and we have trigonal planar. All right. And the last set I'm going to skip on. One thing that I do want to look at here at the very end is the hybridization of those orbitals and showing it using electron configurations. So let's go to a very simple one. CH4, and then another simple one, SF6. And look at the hybridization for these. So carbon, helium, 2s, 2p, 2. We have hydrogen at 1s, 1, 1s, 1, 1s, 1, and a last one. And I'm going to show you that for the next problem, this is not necessary. We don't need to show this. Let me write that out. But for the carbon piece, that's the central atom we're interested in. We know, or we have said several times, that it's the unpaired electrons that do the bonding. But right now we have a paired set of electrons, we have an unpaired set of electrons. And so it goes through that sp3 hybridization. The reason why it's called sp3 is that we're using 1 orbital from the s, 3 orbital from the p, and we hybridize them so they are all now at the same energy level. Therefore, the electrons follow Hund's rule, and then split up into their different set there. So we have the 4 different sites that it can bond. Now, this whole mess here, we're not really interested in. We're just looking at how to write the hybridization. So if we do sulfur here, we have 3s2 and 3p. Four. 1, 2, 3, 4, 5, 6 valence electrons on sulfur. This hybridizes into sp3d2 hybridization. And the reason why sulfur can do hybridization into the d orbital is because the 3rd energy level is the first time that we see a 3d. Oxygen would not be able to do this because oxygen is in the 2nd energy level. And the 2nd energy level does not have a D sublevel yet. So there's this. We end up with sp3d2. So we have 1, 2, 3, 4, 5, 6 valence orbitals and 6 different sites to do bonding. With double bonds, let's just try one with a double bond. Carbon dioxide is, we said, sp hybridized. So we have carbon, again, helium, 2s2 and 2p2. And only 2 of these orbitals are going to hybridize. We have an sp hybridization, boom, boom. There are our first 2 electrons, and then we have pz. Is it pz or is it py? I don't remember. And then pz. And these guys here are unhybridized orbitals. And it has to do with how these orbitals overlap in order to form the bonding. So we have the sp. There's the first 2 sites. Here's the Lewis structure. Those are the first 2 bonds, here, and then the second 2 bonds, here and here. Now, I forgot to do the sigma and pi bonds before. I apologize. Let's just do that here. These guys are going to form the sigma bonds. Those are the first bonds, so we're just going to label whichever one's here sigma. Doesn't matter which one is which, it's just the first bond. And then we go on to our pi bonds. Pi bonds happened from unhybridized orbitals. So the first bonds are always sigma, the second and triple bonds are always going to be our pi bonds. So you can go back and label those in the set before this. All right, so there is the hybridization showing with orbital notation. Thanks, guys. That's it.